This is a simulation on molecule polarity by University of Colorado, phET. This simulation allows you to view the polarity between two atoms, or three atoms, or actual real molecules. To start off with two atoms, you have several options. You can change the electronegativity of the atoms, or you can make them the same. In this case, they would be two atoms with the same electronegativity. Notice how, since they have the same electronegativity, you don't notice a bond dipole. There is also no partial charge. When we take a look at the electron density, the electrons are being shared equally when they have the same electronegativity. However, if I increase the electronegativity on atom A, I'll notice that being more shaded means it has a higher electronegativity, so therefore the electron density is going to be higher. And I'll also know the bond dipole is going to point towards the atom with the higher electronegativity. When I have three atoms, I now can take a look at the bond dipole as well as the molecule dipole. If I want to take a look at the bond dipole, what's happening between A and B and C, I can click this and I see the direction of the dipole that's happening between the bonds. Since atom B is more electronegative than A and C, the dipole of the molecule as a whole is going to point towards atom B. Now when I have a real molecule, I have a choice of several different real molecules. So let's start with the one that they've been given, HF. I can view the bond dipole, or I can view the molecule dipole. I can also view the partial charge, the values of this molecule. I can see what the electronegativity of fluorine and hydrogen are. Then I can also see the electron density. Again, since it's more shaded towards the fluorine end of this molecule, this side of the molecule is going to have a higher electrodensity. Or I can also take a look at the electrostatic potential. Again, this is going to be my more partial negative portion of my molecule, so therefore it's going to have a negative electrostatic potential. If I want to take a look at a nonpolar molecule, I'm going to notice that it doesn't have any bond dipoles because the electrons are being shared equally. It doesn't have a molecule dipole, again, because the electrons are being shared equally. And if I hit electron density, I'm going to notice that it's evenly shaded because, again, the electrons are being shared equally between the two atoms. However, if I want to take a look at a polar molecule, since my molecule dipole is pointing towards the nitrogen end, my nitrogen end is going to have a higher electron density. Let's change this up to formaldehyde. Again, the molecule dipole is going to point towards the oxygen atom. Now, when I get to something like tetrafluoromethane, I'm going to notice I have a carbon atom in which I have 4 fluorine atoms bonded to it. So actually, this is a nonpolar molecule because I have my electrons being shared equally. I don't have one side of this molecule being darker in the gray than the other. Once I add trifluoromethane, I now have a hydrogen with 3 fluorines attached to the carbon atom. I am going to notice a molecular dipole, and I'm going to notice a difference in the electrostatic potential as well as the electron density of this molecule because I'm now looking at a polar molecule. Now this is the simulation. on molecule polarity from phET.